Okay, we're going to welcome Dr. Cressida Cleland to the stage now. So originally from Dublin, Ireland, Cressida Cleland got her bachelor's degree in astronomy at the University College Dublin. She then obtained her PhD at the University of Birmingham in the UK, focusing her research on the evolution of galaxies. She now works at the University of Paris as a postdoc, researching how galaxies and large-scale structure evolved back when the universe was only a small fraction of the age it is now. Questions that Cressida's research hopes to answer include: how did the first galaxy clusters form and evolve? How do galaxies form stars? Why do they stop forming stars? And what will happen to our own galaxy, the Milky Way? So please welcome Dr. Cressida Cleland.
Thank you. So, I wonder how many of you have ever gone outside your back garden on a clear night and tried to take some pictures of the stars. I certainly have. These are actually pictures I took way back in 2013.
Sorry, can you?
Oh, yes.
Sorry. Put on maybe just on your click.
There we go. Okay. We can see on the left-hand side the Milky Way, and there's even a satellite going through that one. The Big Dipper, or the Plough, or I don't know what you call it in your respective language. The moon, and this is actually a more recent photo I took while on an observing trip. We've got Venus on the left-hand side, Saturn in the middle, and Jupiter on the right, all the planets nicely in a line. So yeah, I mean, I've definitely always been interested in looking up at the stars and wondering how the hell does all that work. But luckily for us, we have better photographers now. We don't have to rely on mine or any of our shitty pictures. So as you might have guessed from either the title of the talk or these pictures now, my research interest lies in galaxies, and we can see a nice plethora of some really nice galaxies here. But I don't know if it might surprise you to hear that galaxies actually evolve and change. Now, as astronomers, we can't just look at one galaxy and watch how it evolves through time, because these changes take place over hundreds of millions of years. But we can look at thousands and millions of galaxies and observe trends, not only between different galaxy properties, but even trends through time. As Sophia mentioned earlier, all about redshift, we can observe those trends through redshift as well. So, first of all, let's go back to the beginning. And yeah, so I hope you were paying attention in Sophia's talk, because there will be a test. On the left-hand side, at the very beginning of the universe, we have the Big Bang, which kind of sets up the template for how the universe is going to look in about 14 billion years. And then about 400 million years after the Big Bang, the first stars begin to appear. And then some number of million years after that, we start to see the first galaxies. So galaxies, in terms of the lifetime of the universe, are a relatively new addition compared to where we are now. And yeah, so Sophia mentioned earlier what the cosmic microwave background is, which is good because I don't really know very much about it. But basically, the Big Bang created these perturbations in like the fabric of space-time. And we can measure that using some really sophisticated techniques to get this picture of the density perturbations in the fabric of our universe. And so, in the beginning, the universe was mostly just made up of particles, gas, dust, and dark matter. And in these density pockets, you get more and more dark matter filling in, and the gravitational forces eventually cause those density pockets to kind of merge together, and eventually the gas in those overdensities will begin to condense to form stars. And then it just kind of keeps going from there. More and more stars form, more and more little gas globules get joined into this growing structure, and eventually you start to form something that starts to look like galaxies. And then we can keep going from there. Smaller galaxies merge together to form bigger galaxies, and yeah, so it's just kind of just building up from very small things into the very massive large-scale structure that we know today. And this is known as a hierarchical merging theory or a bottom-up theory, but you know, there's still so many questions about this. This is just the best understanding that we have for now based on cosmological evidence. And then, like I said, we can keep going. So when you have galaxies, they start to gravitate towards each other, and you can form galaxy groups, like tens of galaxies, or galaxy clusters, hundreds to thousands of galaxies. Galaxies can merge, creating even bigger galaxies. Count how many times I say galaxies in this talk, by the way. And yeah, as Sophia showed, these clusters and galaxies tend to form and tend to lie along filaments in the universe, otherwise known as the cosmic web. And I've just got some images here. So the bottom left here is a galaxy cluster. All of these sort of orangey, yellowy, glowing blobs, they're the galaxies in the cluster. But I'm not sure if it's showing up on the screen very well, but maybe you can see there are some sort of like some like streaky lines in the back, or some otherwise like distorted looking galaxies, and that is due to galaxy gravitational lensing. So the mass of the galaxies in the cluster and the dark matter in the cluster is so strong that it's actually bending the light coming from the background, so coming from those galaxies in the background. And so that can help us study even further away galaxies. And then same here, this in the middle, this is a James Webb image of a galaxy cluster as well, but it's kind of hard to make out on this picture, but there's some even more like crazy distorted galaxies that can really tell us a lot about cosmological parameters and high redshift galaxies and the rest. And then on the right is just an image of a simulation of kind of what the cosmic web looks like and what these filaments look like. So, okay, now we have all these galaxies, what are we going to do with them? So about 100 years ago, Edwin Hubble was one of the first to come up with some sort of classification of galaxies. And if we look at this diagram here, we have what we call ellipticals on the left-hand side and spirals on the right-hand side. And the general idea of this diagram here is that it increases in complexity going from left to right. So on the left-hand side, you have basically perfect spheroids, and on the right-hand side, you have these spiral structures with bars or without bars or whatever. So we can play a game of spot the difference, and there are some pretty obvious differences. I think the main one being in color. The spiral galaxy, beautiful spiral galaxy on the left, is very blue, and you can see the structure in the galaxy, you can see the spiral arms, and whereas on the right-hand side, you have a much more yellower, oranger, redder galaxy, lacking in any real structure or defining features. So that on the right-hand side would be called an elliptical or like a spheroid. I like to call them blobs, but you know. And so the reason that the blue color is only found in spirals is because the blue color comes from the newly formed stars. So the newly formed, really hot, young, energetic stars, those give off blue light, whereas as the stars get older, so long as they don't die first, they stay redder. So that's why older galaxies are red, and we call them dead galaxies because they're not forming any new stars. We also have irregular galaxies that don't really fall into this spiral elliptical classification. These are often quite small galaxies, low in mass, quite faint, diffuse. And these can be formed in like a lot of different ways. But so these can be formed by the effects of strong gravitational forces in like high density environments. Or from merging. And so merging is what happens when galaxies clash together in a really violent event. And I'm putting this here because A, it can cause these kind of weird looking galaxies, but B, merging can also be a quenching mechanism. And quenching is the name given to when a galaxy dies, basically. Quenching means a galaxy is stopping forming stars, so if a galaxy is dead, it's also considered quenched. I'll probably say quenched later on, so make sure you know what that means. Okay? Yes, so yeah, here are some quenching mechanisms. This was basically what I did my PhD on. I'm not going to go through them all now because I don't think you want to hear me talk for another hour, but basically there are 4 main camps. So quenching can either happen slowly or quickly, and it can either happen kind of depending on the properties of the galaxy itself, or depending on what's happening around the galaxy, so like environmental mechanisms. But the problem with quenching is that all these things are interrelated and dependent on each other, and it makes it really hard to study because, you know, you don't know which of these mechanisms is more important than the other or whatever. So if we go back to our spiral and our elliptical, you might be wondering, okay, so if a galaxy quenches, it goes from the left to the right, kind of. But the problem in observational astronomy is that we don't really see many galaxies in between these things. Like, how does that go to that? And the answer is we don't really know yet. There's not many galaxies, and that's why we call it the green valley, because it's like a valley between red and blue. And this is a really active area of research, again, one I spent a bit of time on in my PhD. So, what can I tell you about how galaxies die? There are some main points that I can cover today. So the first is that the higher the mass you are as a galaxy, the more likely you are to be quenched. So if we look at this plot on the bottom, that's from my work, as you go to the right-hand side, you're going up in mass, and as you go up, there are more galaxies that are dead at that mass. So we can see that as you go higher in mass, there are more galaxies that are quenched. The plot on the right-hand side, if you just focus now on going from left to right, again, as you go to the right of the plot, the higher mass you are, the more red galaxies there are. So again, the more quenched there are. So this seems to be a pretty important thing in observations. Another thing is that the denser the environment you're in, so how many galaxies there are around you or how big the cluster you're in is, again, the more likely you are to be quenched. So it's the same plot on the right-hand side because this is a very clever plot. They have it on both axes. So this time, if you go from bottom to up, you're going from a low-density environment to a high-density environment. And again, you can see that there are more red galaxies up at the top in the high-density environment. And in this plot here, as the lines go up, so you can see there's different lines there. As the lines go up, that's like more massive groups and clusters. So you can see that in a more massive group or cluster, there's a higher number of dead galaxies. So yeah, denser environment, more likely to be quenched. And finally, one of the things I'm just going to tell you about, if a galaxy has a supermassive black hole in the middle of it, which a lot of them do, then there's theoretical evidence that this can do a really good job at killing the galaxy. Difficult to find direct observational evidence of this, but we can definitely see the correlations. So again, if you're a more massive galaxy, then you're more likely to have a more massive black hole. So kind of correlations there between massive galaxies being quenched and a more massive black hole. And then this is an observation of radio emission from a supermassive black hole in a galaxy. So that radio emission can actually expel the cold gas that you need to make stars. So if you get rid of the gas, you can't make stars. And again, there's a lot of other things going on here, lots of questions. I mean, this is a hugely active, and also I've only kind of touched on things in like the local universe, because that's what I did my PhD on, but there's a whole nother kettle of fish going on at higher redshifts. So, take everything I say with a grain of salt. Okay, here we go. This is, I left this in as an old slide because I thought it was interesting because this is pre-James Webb. So I said, okay, James Webb might answer, what did the first galaxies look like? And now I can actually kind of show you. I mean, they don't look like much, but there's these little red blobs. And over the past 8 months or so, almost a year of James Webb being operational, we've now got this whole gang of high redshift galaxies that are, to be honest, completely messing with our understanding of galaxy evolution. Like, some of these galaxies, according to our current theories, should not exist. So it's exciting, but also kind of annoying. And then finally, I mean, this is the actual future slide now. So yep, Euclid, which is what I work on now. And yeah, this is going to just unlock so many doors for us to look into high redshift galaxy evolution, and how large-scale structure evolves alongside that. And also LSST, which is a all-sky survey that's aiming to cover the whole sky every 3 nights, I think. 1 night or 3 nights, I can't remember. And so yeah, being able to just watch galaxies like every single night and see what they're up to. Together, these 2 surveys are going to just blow the whole thing open. We're going to have so many new things to look at in a few years' time. And that is me.
Okay, does anyone have any questions that you'd like to ask? All right.
That really fast. No, perfect. That was perfect.
Thank you very much for the nice talk.
Maybe just use that one so everyone can hear.
So, what is the lifetime of us living here? Because you talked a lot about like getting killed and quenched and things.
Okay. Yeah, I know. Sorry guys, you don't have long. No, as I said, these things take millions, hundreds of millions of years. But the Milky Way is actually kind of an interesting case. It's some people think that the Milky Way is one of these Green Valley galaxies, in that it's still a spiral galaxy. It's still like forming stars and things, but it looks like the star formation rate has slowed down a little bit. So, but I mean, it's kind of much harder to do these observations from within the galaxy. So this is all kind of ongoing, but there has been some evidence to suggest that the Milky Way is slowing down. So if that's the case, we're talking 500 million years to a giga-year. But I mean, maybe someone knows. I don't know when Andromeda is meant to merge with the Milky Way. Is it on that time scale? More than 1 million. Maybe 100 million. I think Andromeda is the Milky Way's biggest threat right now. But again, we're talking like hundreds of millions of years. But yeah, the Milky Way maybe on its way out soon.
But not us.
Also.
When you look through the telescope and you see these little blobs in the sky, what is the criteria that says, oh, that's a galaxy, that's not a galaxy? Especially these little ones that are really far away and you can't tell, are there stars there? Is it just one star? Or like, what is the parameter or criteria that says galaxy not?
Thank you. Yeah, so I mean, it's not exactly my field. So again, if I say anything wrong, step in. But as far as I'm aware, with these James Webb galaxies, there were like dozens popping up within the first few weeks of the data being available. People just being like, oh my God, redshift 13 galaxy, redshift 14 galaxy. And they were all done using photometric measurements, which aren't as reliable. So really, to confirm these things as galaxies and as the redshift that they're at, you need the spectra, which just takes a bit more time and comes in a bit later. And so I did my best when I was looking to put those galaxies in to find ones that were definitely confirmed. But yeah, you would use the spectrum of the galaxy. When you're taking observational astronomical images like that as well, galaxies and stars do look very different because galaxies are like extended sources, stars are point sources. So that's how we know they're definitely not just lone stars. But to actually confirm that they're at the redshift they're at, yeah, you need spectra, which is just a lot more expensive at that redshift, but absolutely possible in this era. So yeah, watch the space, basically. Yeah.
How do you distinguish between what is quenching the galaxy? Is it, so you said that black holes can quench it. So how do you know if it is just the galaxy being massive leading to the quenching versus the black hole causing it? What is the cause and effect mechanism?
Yeah, that's a really good point that I didn't really mention. So the thing about the galaxy being massive quenching, that generally does mean that the black hole is doing the quenching. So as a galaxy gets more massive, its black hole gets more massive, gets more active, and will lead to quenching. So, but it's not like that's a one-to-one. It's just kind of like, well, we see all these massively quenched galaxies and we know this is a thing that can happen, so that must be what's happening. But there are other ways that you can, basically mass quenching is just kind of an umbrella term that we use for anything we don't know. But so it's kind of like, there's not really an easy way to distinguish, but it's more like, we know theoretically this thing can happen and we see the empirical evidence that it's happening. So generally when people talk about high mass galaxies being quenched, they just they mean that the AGN, that the black hole might be quenching it, but we don't really know for sure.
Hi, thank you for a nice talk. I arrived 15-20 minutes ago, so I don't know if you explained this or not. But when you were measuring the rate at which galaxies evolve, so how fast they age, and that there are older galaxies and younger galaxies, I think that depends entirely on the stellar population, what type of stars you have, and basically the mass of the stars, which is, I think, the only thing that determines how fast it's going to die. So my question is, do all the galaxies start from the same point, meaning that it is assumed that all the galaxies start in the beginning, they all start with the same kind of stars, or the same kind of mass, and so it's just a matter of time. But they are all going to evolve the same way because they study with the same type of star, the same these are statistics or.
So to put a disclaimer first, galaxy formation is not really my field at all, but I think the answer to that is no, they don't all start the same. It will depend a lot on the environment that the galaxy is found in. Like if it's in a low density environment or a high density environment, it'll depend on what kind of gases are already in the environment. So that, like, we call the metallicity, how metallic the stars are is going to have a very big impact on how long they survive. But really, I think what's underpinning the lifetime of the galaxy is its star formation rate. How quickly is it using up its gas to make new stars compared to how quickly can it replenish that gas from outside the galaxy? Yeah, I think that more so than just the stars being born and dying, it's more about what's happening to the gas in the galaxy that can either sustain it making more stars for a long time or prevent it from making more stars.
Thank you very much. I had a question about the Green Valley problem. And I guess naively you would sort of think, okay, these sort of processes happen over hundreds of millions of years, and you would expect to see sort of all the stages represented in surveys. Does the fact that you sort of see one state and then another state and nothing in between imply that there's sort of a rapid decay or a rapid shift from one to the other, and that's why we don't see? I mean, you said there's no answer, but
No. I mean, you've basically hit the nail on the head. Are you sure you're not a galaxy evolution person? I could send you my PhD paper. It was basically exactly on that. Yeah, so that's exactly it. The fact that we don't see many of these galaxies implies, and this is what it's called in the literature, a rapid then delayed quenching mechanism. Delayed then rapid quenching mechanism. So that means that the quenching, the thing that causes the quenching might happen, but then we don't see the quenching until several million years later. Or at least that's one. As I said, there's lots of mechanisms, but this is one of the most common ones. And yeah, I mean, 500 million years, it's quite a short slice in terms of the lifetime of a galaxy and the entire universe. So it is just a question of like, can we look in the right place to find these things? But you're exactly right. In general, again, for one of the most common quenching mechanisms, it implies a very quick switch. Yeah, exactly. Yeah, I hope that, yeah.
But you are saying that you are witnessing Green Valley galaxies, or you are not sure about, like, you know Green Valley galaxies?
So yeah, I mean, there's a couple different ways to identify these galaxies. Again, they're just not as common as the other kinds, but we can set constraints to hope that we have found them, if that makes sense. So one way is by using color. So every time I mention red galaxies, blue galaxies, I literally mean red and blue, like their light looks red and blue. So we can create, so if you imagine if you imagine a distribution of color where you have like red up here, blue here, you just say, okay, I want everything in between. And it'll be a lot less, but it'll be something. And then you just look at the properties of those. In my work, we used a kind of sophisticated technique to identify galaxies that had recently quenched, so as in their star formation rate had recently stopped. And yeah, we found similar things, these kind of mass trends and environmental trends. So yeah, there's ways to set constraints so that you hope you're finding a Green Valley galaxy, but again, it's just like, you have to trust that your constraints are looking for that exact galaxy and you're not contaminating your sample in any way. So yeah, they do exist, there's just not many of them.
Thank you very much for your time. Thank you. You said something at the very end of your presentation about how with the new James Webb telescope we see galaxies that shouldn't exist. Can you tell us a little bit about what about them exist? Thank you.
Yeah, again, just a caveat, it's all very new things and not exactly my field, but I can tell you what I've read. So one thing about some of these high redshift galaxies, I mean, you just simply need the time to have built up that much mass to be a galaxy, which some of these struggle to have existed for that long. But I think what's more compelling to me, as someone who studies quenching and stuff, we're finding very high redshift galaxies that are already quenched, which is kind of an interesting thing because, again, you need to have spent the time to have already like built up all your mass through star formation. Remember, these galaxies don't just like pop in at the mass, they have to build up that mass and then they need to quench. And I've already mentioned how quenching takes like a couple 100 million years. So basically the buildup of the galaxies and the decline of the galaxies is all happening very, very fast and much faster than we would expect under our current understanding of galaxy formation. But I think the answer will be found out soon enough. I think it's probably just a failing in our part on understanding how these things happen. But yeah, they're really interesting objects for sure. Probably, yeah.
Okay, thank you, Cressida, and thank you everyone for the questions. We had some really good questions. I appreciate all of them. Let's thank our speakers again. All right, thank you all for coming. Again, we have, we're on Instagram and Twitter and Facebook, and we have a webpage, so please follow us. And the mic, yes. We will post for our next event, which should happen next month sometime at the end of November. So thank you all for coming tonight. We really appreciate it. Have a good night. Thanks.